of 8.1 and 8.2 for growth modeling, decay modeling, as well as some principal interest problems we're going to look at. What's that? No, I just said 8.1 and 8.2, you know. Listening's hard. When we get...
I can't turn it like me.
So, what these become are actually pretty easy, real-world application-style word problems. They make a ton of sense. You guys are going to use these a lot. You've probably used these before. I know, like in chemistry, you guys talk about radioactive decay, carbon dating, or something like that. At some point in time, you will. You'll look at if you've taken finance before. You're going to talk about interest, how that's compounded when you're talking about savings accounts. When you guys buy a car at some point in time, cars and things like that depreciate. So things depreciate at different rates, knowing how what things are going to be worth and whatnot as you go along. This is actually makes sense to learn. It's quite easy. So we're going to look at what are called growth models to start out with. And you have these things called growth models. And an exponential growth model has the following. Y equals some initial amount. So this A value is your initial amount. R is your rate. It's always written out as a decimal. They're going to give it to you in terms of a percentage. You just have to convert that to a decimal. And then your T is some value of time. It's usually years. Okay. The stuff that's in the parentheses, that 1 plus your rate, is called the growth factor. So if you start to look at that, that value in the parentheses becomes your B value of an exponential growth problem. So this mirrors the same idea as y equals A times B to the x, where this B value is that. That's all. That's all it is. That's all it is. And by being a growth model, your B value is always greater than 1. The decay model, your B value will be less than 1, so we'll be subtracting the rate when I show you that. Yes, sir?
Why is it there a 1?
Because your growth model is 1 plus something. So remember, your B value is always greater than 1 for growth.
Mm-hmm.
Your B value was less than 1. 1 was K. That's why.
What if R was a negative decimal?
You're not going to have a negative. You're not going to have a negative decimal because that means it's still decreasing at a slower. It's still a decreased percentage. You're not going to have a negative percentage.
Still, even if you add the negative decimal to 1, it's still positive.
Right. So let me show you guys this really easy example. Population. Population stuff show up all the time. Where they talk about a certain population of a town is modeled after this. I think so. When you're looking at this style of problem, these types of word problems a lot of times are just going to give you the model. You don't need to come up with it on your own. They're going to say such and such information is modeled after this. Do something with it is what they're going to do. Okay? In this example, it says that the population of this town since 1990 can be modeled after this. So what is the original year?
1990.
So that's your year 0. Okay? That's your year 0 when it starts. Because if your year is at 0, that means your T value is 0. What's anything raised to the 0 power?
1.
So what's your initial amount then?
6,791.
That's how this falls into place. It falls into place that easy. So your initial amount, that A value, would be 6191. That's how many people were there in 1990. That's the beginning year, year 0. By what rate is this increasing?
1.04.
Wrong. 4%. So your rate is a 4% increase. The growth factor is that 1.04. That's that whole thing in parentheses, okay? And that's usually what people will do, because they're not accustomed to seeing it ask that question like that. Val, what's wrong? You're giving me this crunch face.
Wait, where did you get 4% from?
You notice how it's 1.04? So that means that this is 1 plus 0.04,
Oh, I get it.
okay?
Yeah.
And that's how they do this a lot. They write it all out, they don't put that plus sign in there,
Okay, that's.
okay? So your rate's 4%. I'll tell you one thing, usually what people screw up with that is that if they'll, instead of writing it at 4%, you write it as 0.04%, which is not quarters. You know, you'll mess up your decimal there, so just be careful. By what percent we did all that, did that. So what would happen if I wanted to know what's the population in year, let's say, 2007?
2017.
So what would your T be then? 17. So what do you think you need to do?
You should calculate.
You have to use your calculator, because you can't do this without a calculator, can you?
Wait, I can't understand that part. How did you get to 17?
Year 0 is 1990.
Okay. Oh, okay, yeah.
All right. So now when you substitute that in, it's just a matter of literally writing it out the same way. What was it? 6191 parentheses 1.04 to the 17.
Yeah.
And that means they have roughly 12,059 people in that town in 2007. Now, this is where it comes in to make sure you round correctly. You're not going to have half a person. You usually want to round to the nearest whole person.
How does math get this happen?
What if this little person comes out?
No.
This is a short person.
They're like half the size of a regular.
Okay, but just a little person.
Okay, if people can aspire to have a family with 2.5 children, we can be right. 12,059.
Wait, what are you talking about?
I don't know.
The average amount of children was, at one point, it was like 2.5 children. I'm like, how do you have half a child? Well, you can have half a child. Exactly, there you go.
Back to more minute. All right. So, anywho, here's the other one we're looking at today. This is a compounding interest style problem. Good old banking. So we get a growth point at y equals your initial amount, 1 plus your rate to the time. So this is your interest problem. Big difference between using a model like this versus the other ones. An exponential growth model is just straightforward. They're going to give you some model. Here you're talking about things with money and interest. Now, you guys ever heard of a thing where they're talking about compounding interest? You know what it means to compound?
You put two interests together.
Yeah, pretty much, if you want to think of it that way. What happens here is if you're talking about some interest being compounded, interest can be accrued certain ways. Annually, daily, quarterly, monthly, or whatever, depending upon how the bank sets it up. What happens here is it's that compounding means is how many times within a calendar year they're going to add your interest in. Okay, that's what that compound means. So as you go through this, what are all these values? This means that some amount is equal to your original investment, your principal, how much money you start with, again, same thing as your initial amount. Your R is still your rate as a decimal. This N value is the number of times it compounds. And the problem will tell you. And then T is your time in years. Okay. These are very, very easy to work with. So you have some original amount, your principal, 1 plus your rate divided by n to the n times t. Very, very easy example. Starting out a check or starting out an account with $1,000. compounds annually at 8%. Deposit $1,000 into an account at 8% interest. Find the balance after a year when it's compounded in different methods. So if I say it's going to compound annually, how many times does it compound? Once. So that would be n would equal 1. If I say it's going to compound quarterly, how many times would it compound? 4 times. If I say it's going to compound daily, 365.
0.25, right?
Nah, they just do this for that one. Obviously, if it's a leap year, they put 366, but in this case. Now, just by thinking about it numerically, what do you think your best bet would want? What would you want your money to be invested at?
Daily.
Why?
Because you get 8% of it every single day. That'd be a lot of money.
That's a lot.
Well, remember, it's, okay, I'll show you how this works. Okay.
No, you want it
Quarterly.
lowest, right?
What is
Like,
8% annual no
Some
matter what?
things, and I remember I got really bad interest, but it wasn't very high or very low.
Hey, you're right, because it's not a lot of money. It really isn't a lot of money.
You don't want it high, right? Because not like how much they, never mind.
Wait,
I'd
because
rather have a quarterly.
Well, let's use it. Now, remember, you're using the same model for all of it. The only thing that's going to change is your value of n. So it's your overall amount is your principal times 1 plus your, what was our rate? 0.08 divided by 1 to the 1 times 1. That's for the first part, for part A. Now, I know that I don't need to have that divided by 1 to the 1 power and all that. I'm oversimplifying what it's going to look like to put in my calculator. Because I'm going to be using the same values, but I'm just changing the number of times it's going to compound. So I'm going to type it all in my calculator now and just overwrite it later. You guys have done that before, right? I'll show you. So let's go to our calculators and put that in. So we'll see, it was 1,000, parentheses, 1 plus alpha y equals 0.08 over 1. Close it to the 1 times 1. So basically, this problem is your first year you're getting 8% interest on $1,000. So that means you make $8.
yeah, wouldn't you want it daily? Because then you'll get 8% interest on $1,080, and then 8% interest on 1,080 is 8%, and then so on. And so
Yep,
on,
and it
right?
compounds out. Yeah.
Yeah.
So as you go through that, your first value you get $1,080. If it goes to quarterly, let me show you how to overwrite. Do you guys know how to pull up the last thing you typed in the calculator?
Yeah.
How?
Enter.
You hit second, enter.
I didn't know that.
Yeah, it's a nice little trick. Second, enter, we'll pull up the last thing you typed.
Or you can just do it in y equals and go back.
And then in this case, I'm going to change my denominator to a 4 and one of the ones in the x one to a 4. And just by moving the left button. Yours is a lot faster to do this than it is for me on this. And I hit enter. So if it compounds quarterly, I make a whole whopping $2 and change more.
Yeah.
Woohoo! We go to Sizzler, we go to Sizzler. Neighbor movie for 1 million points.
Dang, I need that to be cold.
Wait, what is this
Can you sing it again?
again?
We go to Sizzler, we go to Sizzler. Nobody cares, thanks. Sorry for,
That was rude.
Titanic. Avatar.
American
The
Graffiti.
Godfather.
The Sandlot.
Part 2.
anyway, and then we'll like change this to get to the last one.
365.
365. Do you see how very easy it is once you get the version of formula thrown in there?
Do we have to round these ones?
What's that?
Do we have to round these ones?
You're dealing with money, so what are you going to round it to?
What is that? How does
Always round it. When you're dealing with money, you round it to 2 decimal places. Ooh. Let's read that up. Nah, whatever. It's only like, it's like 1083, I think.
1083.27.
It's not that much more, because remember, what's happening is that you're multiplying it by that same rate divided by a larger value, so it's not that much of a difference,
Oh, yeah.
okay? Because that value is changing as well.
Technically, it's 0.28 because you round it to the thousandth place.
Yeah.
So, principal interest style problems are extraordinarily easy to work with. It's just a matter of looking at how many times they're compounding over how many years. Okay, that's the only thing that's going to change. So in this one here, let's do this at 20 years, compounding quarter. Just do that quartering, $500 in an account, 3% interest annually, compounding quarterly for 20 years. See how much money you'll have. Take a minute to do it. So let's see, in this one you're doing $500 was your initial. Put this out. 500 was my initial. Parentheses 1 plus 3%, so it's 0.03. Oops. It was quarterly, so it's divided by 4. And then my exponent would be 4 times the 20. $900, $909.02.
Yeah, it's a lot more.
So after 20 years, that account, yeah, it was after 20 years, right? Okay.
I went to and I got home and I was like 5 minutes and it was terrible.
Actually, when I
Just
got
barely.
like, honestly,
Smidge.
I was nasty, so I had to wait for my dad like an
So, like I said, guys, this isn't a really difficult scenario to work with. It is actually pretty easy. You're using your calculator through all of it, just a matter of making it work. Okay? Question on that? All right, let's look at decay. The only difference between growth and decay is that now
it is a negative fraction, that's it. Negative decimal.
it's 1 minus the rate. That's it. Because once again, think about it in terms of exponential growth, exponential decay. Your growth values your B values were always greater than 1. Your decay values, the D values were between 0 and 1. That's how you get it between 0 and 1. So this is growth. This is dealing with money. And this is your decay. Your A value is still your initial amount. Your R is still your rate as a decimal. T is still your value in terms of time. The decay factor is that symbol, whatever it is in parentheses, whatever it might be. So it's really easy to tell the difference between the two. So it's Y equals which one of those is growth? Which one of those is decay?
The top one is growth.
Why?
Because the top one's greater than 1.
All right. So what is the rate in the top one? What's the rate in the bottom one? 63%.
I can't spell that fast.
Remember, it's 1 minus the rate. That's how they're getting that to you, okay? And so you have to work backwards out of that one. All right? It's very easy to work with. Again, it's not that we have to worry about trying to graph or do any of these things. A lot of these things is a matter of just going right into your calculator, sometimes looking for the table stuff, okay? Yes, ma'am?
So if like inside the parentheses greater than 1, it's growth, less than 1, it's decay.
Yep. Because remember, it mirrors the exact same thing of A times B to the X. So B is greater than 1, growth. If D is between 0 and 1, it's decay. It mirrored the same thing as the other stuff, and your parent function. These are all just parent functions with words.
I have trouble understanding the bottom of the two. Is that basically saying if it's between 0 and 1, it's
That's all it is. That's all it means. Okay. That's all it is. All right. Now, when we look at a word problems with these, this is where it comes into being a lot of depreciation style. When you buy cars, when you buy durable goods, you guys know what it means to depreciate? Loses value. You know, like when you buy a car, the minute you drive it off the lot, it's worth less than what you bought it for. All right. Eventually, there's a law of diminishing returns where it's going to be still worth. I mean, it's not going to be worth nothing at some point. I mean, it'll still be worth whatever the weight of steel is worth.
It's worth money.
They're going to pay you to take it away. Right?
Yeah.
So, really easy one to work with is you're buying a car for 24 grand, and they say that it depreciates at 16%. Write out the model and figure out what it is, what's it worth after 2 years. So when I'm writing out the model here, that means, well, what's your initial amount? So your initial amount is 24,000. What's my rate? 16%, so 0.16. And what's my time? What are they looking for at 2? In this case, we're looking at it at 2. So if I want to write out the model, what's the equation? Well, y equals 24 grand. 1 minus 0.16 squared. Now, this problem has 3 parts to it. The second one is graphic. I'm not going to have you guys graph these growth ones or decay ones. It's a bit of a pain. So there's no reason for us to. You get a lot of weird, really weird, funky looking stuff. So you don't really need to worry about graphing them. What I do want to do, though, is put these into our y equals and change that 2 value to the variable. Because then we'll be able to look at all values when time is changing. Okay? I'm sorry, I'm using t. So let's go to our calculator again. Go to your y equals and type it in exactly the way it's written. You don't have to do the subtraction, the 1 minus the 0.16. You don't have to put in the simplified growth factor if you don't want to. Calculator will do it for you. Well, the first question was, what was it after 2 years? Well, what was that car worth after 2 years? 16,934. All right.
Probably don't type in T.
Yeah, and that's right. I mean, I could talk about this all day today. There are some cars are never going to be worth anything in time. Some cars they're going to depreciate and then grow right away, or some cars appreciate right away. You know? Yes, sir.
Does it really go down by 16% each year?
Depends on the car. Seriously, it really does depend upon the car and the style and all that. There are certain cars and trucks and stuff that depreciate faster than others. Do you guys know which ones depreciate the fastest?
Ford trucks.
No.
Because they're very big.
Ferraris.
One's
Green
with 4 wheels.
SUVs.
Honestly, the ones that tend to depreciate more are ones that aren't rated as highly as others. Dodges, Jeeps, Rams, things like that. Chryslers. They tend to depreciate a lot faster than like a Toyota or a Honda. You know, back when gas was $4 or $5 a gallon, SUVs, an SUV, you drive it off the lot, it was worth half of what you paid for it. You know, it was great investment back then. But for those of us that bought, I mean, this is when we bought, before we had our pickup, we had a Suburban. And we bought our Suburban when gas was $4 something a gallon. And people were like, why are you buying a Suburban? And I go, because I can afford one right now. Because we bought one that someone had already, we bought it used. Somebody took the depreciation hit on it. So brand new, the Suburban would be so expensive. When they traded it in, it was worth less because people didn't want to buy it because of the gas prices. So there are times when buying a used vehicle are better for you than buying a new one. You see that a lot. What's that?
You were thinking probably like those schmucks paying for my car.
Yeah,
'Cause that's kind of what they're doing, right?
it's not so much. Yeah, I mean, when you think about, you guys have heard the term underwater, like on mortgages and things like that.
I don't even know
Well,
mortgages.
being underwater on anything that you are making payments on. If you're buying a car, let's say you buy this $24,000 car. In 2 years, the car is only worth $16,900. You probably still owe $18,000 on the car at that point in time, because the way the interest is daily interest is accruing upon your loan. So if you traded your car in, they might give you, if they say it's worth 16, so the car dealer will give you 14 because they want to make a profit. But you owe 18, so you're underwater $4,000 on your car. So it's not that you're still trading your car, but you still got to come up with that $4,000. Usually that gets rolled into the next one, so you're underwater even further. That's how a lot of the financial stuff, when people were buying things that they couldn't really afford earlier on, that's where a lot of it went in. Yes, sir.
If you can maintain your car well though, after a while the TK becomes gross, once it becomes like a classic or something.
That's what Lydia was just saying here. I mean, it also depends on the car. I mean, my wife's car, our Jetta, it just turned 100,000 miles over the weekend. It's not going to be worth a lot of money. I know it's not going to be worth an exorbitant amount of money, in another 10 years. It'll still be worth $4,000 probably in 10 years, because it's probably only worth like $5,000 right now. It's because sheet metal is still worth that much at some point in time. Whereas, if you buy the new Vet, you're paying $70,000 off the door right now. You could probably sell it for what you paid for it. There'll be a depreciation eventually on it, but eventually, if it's more one of the limited style versions of it, it could be worth $100,000 at some point in time. But it's ebbs and flows in the market values and stuff like that. Ferraris, people are like, Ferraris are great investments. Oh, maybe. Depends on which one you get. That kind of thing. So. It's just money. Just spend all of it. You don't need any of it. In this case here, the second part of this problem, it said approximately when was the car worth $12,000. You're just scrolling through. Looks like, what was it? Somewhere between year 3 and year 4. So it had to make that jump somewhere at the end of the third year. So you would say, I don't know, November. All right. That's what you're looking at being able to do. Yes, sir.
Mine always shows this.
Then you put it in as linear, and you have it as exponential. Because you have it as a square, you didn't change that to x. That's why. No. Okay. Does that make sense? Pretty easy stuff to work with. Okay. Like I said, this is really the practical use of growth and decay modeling. When we get into the values of E, the number E, tomorrow, you'll see some more of this stuff where it's a continuously compounded. It's another style formula, which you've probably seen as well. People have been asking me about quiz stuff for this week. What it's looking like since we've gotten through 8.1 and 8.2, the 8.3 word problem stuff, or this 8.2 word problem stuff is relatively easy. 8.3 has the same idea where we're going to grab stuff, some exponent rules, and some word problem in it. That might take a day and a half, so it gets us through Wednesday. We might be able to, depending on how it goes tomorrow, we'll probably be able to quiz Thursday, Friday at the very latest over the first 3 sections. I'm thinking to probably do it Thursday. I'd like to, because when we start logarithms are really easy to start with because there's some rules. Yes, sir.
Are these like the only difficulty that this stuff's going to be in order to get harder?
It depends on how good you are at word problems. Do those, please. Yeah,
We have a calculator and a non-calculator parts. Will
yes,
they
we
both
would.
be on the same day?
Yeah, we would both be on the same day. It would be the graph would be the non-calculator. This stuff would be calculated.
Are both of those no graphs?
Yes, what happened, just like that last problem I had where it said the middle section said graph it, there's a couple of these problems as they're listing them out. Like 43 is what's the model, 44 is graph it, 45 is solve it for this. So I'm telling you, don't worry about the graph
Well,
part.
the 56 through 66, is that also in the graph?
There's no graphs in those problems to worry about. Those are your interest problems. This shouldn't take you more than 20 minutes, guys. It's really, really fast stuff. All right.
You said like when we were going back like the 0.37 where it's 63%. How does it become that? And then the problem we just had where 0.16% represents 16%.
Because that one was bless you.
Bless you.
In that it's running back and forth. When you did this, that's 1 minus 0.67. which equals which equals 0.37. So this is your rate. They just simplified it. I usually write it out as just 1 minus 0.6. I just need
No, but that would be a better, because I just took
Yeah, and the book does that too. The book will do that where, like here, see how it says 0.39? It says 0.39, so does that mean it's growth or decay? It's decay, so the decay factor is 0.39, but the decay rate is, very good. That's exactly what it is. Does that make sense? Good question.
Can I ask a question, so I was writing up the numbers when you were talking about that?
Yeah.
What's no graph speed?
Oh, just like the problem we did there where I crossed out the thing that said graph it, you're going to see in these problems where it'll say, on number 43, it'll say